This call is now being recorded. Yeah, good morning to one and all. Myself, Samuel Gemsprim, working as assistant professor in the Department of Automobile Engineering in Hindusthan College of Engineering and Technology. Today, I'm gonna share a few things, few basics of fluid mechanics along with hydraulics and pneumatic systems. So this session is specifically on basics of some basic concepts of fluid mechanics along with hydraulics and pneumatics. First of all, I would like to greet every one of you who are watching this video to have a pleasant morning as well as have a good day. Today, as per our schedule, we are going to see some of the important topics. First, we have the pressure and measurements. Second thing is we have Bernoulli's theorem, which serves as an important theorem in many of the fluid mechanic applications along with its applications. Then turbines, pumps, these topics are covered under fluid mechanics, followed by we also gonna discuss about the hydraulic systems and its associated components and pneumatic systems. So these are the various topics which we are going to cover in this particular session. And first, without wasting much of time, let me get inside the pressure measurements. So the pressure measurement. So as we all very well know about, pressure means force acting per unit area. So it is in fluid mechanics, it is a force which is exerted by a fluid on a surface of the container or the fluid itself. So this is the concept of pressure in case of a fluid mechanic systems. So here to demonstrate the same, we have the particular example. So we have the working animation there. You can able to see, since the pressure of fluid is more, in the bottom of the can we can able to see more velocity, and just above that we have comparably lesser. And when the height goes upwards, that is when the pressure is dropping, obviously the velocity is also dropping. So this serves as a good example for pressure in fluid. Basically we have different type of pressures as per the system. So first of all, if in an environment, if there is zero, that is no vacuum, no pressure, anything, nothing is there, in that situation we have it as absolute zero, so which is at the bottom side we can able to see. And just above it we have the absolute pressure, which is from the exact zero, which means from the vacuumized environment to a particular measured value is known as absolute pressure. Then we have the local atmospheric pressure, which also considered along with vacuum pressure. Okay, so when absolute pressure is considered also with vacuum pressure, then it is termed as local atmospheric pressure. Then above all these, that is with considering the atmospheric pressure, if we measure anything in a pressure gauge or anything, so that is known as gauge pressure. So in our practical atmosphere, whatever the things we are measuring, say for example in our laboratory conditions, we use pressure gauge to measure the pressure of any given system. Okay, for example, if we have the vehicles, obviously we'll be checking the tire pressure using a pressure gauge. Okay, normally it is measured with the unit PSI, pounds per square inch. So in that case, so if it is 30 PSI, it does not mean that it is exact or absolute 30%, because in the environment where we are living, we have an ambient atmospheric pressure value. Regarding that value, we will see in a short while. So we are considering the tire air pressure, that is 30 psi, apart from or without considering the atmospheric pressure, which is omnipresent, okay, which is present everywhere. So we are not supposed to consider it in the case of the gauge pressure. So this serves as a good example for difference between gauge pressure and atmospheric pressure. When all these values are considered together, then it is known as total absolute pressure. When all these values are considered together, then it is known as total absolute pressure. Yeah. So basically the pressure can be classified into two. One is static pressure, whereas the other one is dynamic pressure. So as we all know about the terms static and dynamic, so static in the sense if the pressure is constant or static or it is not varying, that is what meant by static. Okay, the pressure is said as static pressure. A good example is if balloon, if it is filled with air, so obviously there nothing is changing. Okay, simply the pressure makes the balloon to get formed to the particular shape, thereby it is floating where we used to play with it. So in that case the pressure is unvarying. Once if the pressure is filled, then it is not varied. So that is static pressure. And dynamic pressure is as shown in the animation, we can able to see the wheel is continuously rotating. So in that case, even in our vehicles, we have seen that the bottom side of the tire, obviously it is getting pressurized. So during that particular value, the pressure is a little varying inside the tire. Okay, so this is a good condition or good example for dynamic pressure. So the vehicle's load when directly acts on the bottom side of the vehicle tire, obviously it deflects more, and there the area, cross section area reduces, thereby the pressure increases. And when the tires, that particular part goes upwards, slowly or gradually the cross section is increasing, thereby the pressure also reduces. So here in this case there is a continuous variation in the pressure. So this is known as dynamic pressure. Then as I told you, the atmospheric pressure, so from absolute zero to the omnipresent atmospheric pressure value, so that is at sea level 14.7 psi. Okay, so just for example I am telling you, so if in my bike, if the tire pressure is 30 psi, gauge pressure is 30 psi, but the absolute pressure is this 14.7 plus 30, so it is by total 44.7 psi. I'm talking about the absolute pressure, total absolute pressure, which means I need to also consider the atmospheric pressure value. Okay, so that is 14.7 psi, or in other units we have 101.3 kilopascal or 760 mm of mercury, 10.3 meters of water, or 1013 millibars. Okay, so just for reference, I have shown you the commonly used or commonly known units. First unit is Pascal. 1 Pascal is 1 Newton per meter square, and 1 bar is 1 into 10 power 5 Pascals, or 1 into 10 power 5 Newton per meter square. Okay, then let me give the glimpses of what are the various pressure measurement systems we have. So first of all, we have the mechanical kind of devices which are used for pressure measurement, and the other sense we have the electromechanical devices. So the most commonly used or most effective and efficient type of pressure measurement systems are based on mechanical systems. The electromechanical systems are mostly associated with any of the electronic components for electronic actuation. So only we are going to concentrate on the mechanical type of pressure measurement systems or devices. So to measure the static pressure, we have manometers. Manometers are the basic type of equipment where it uses the fluid levels, whether it is water or mercury. There are two standard fluids used in a manometer. One is water, whereas the other one is mercury. So any one of these fluids are used in order to check the value or level. Thereby, very easily we could able to find out the difference in pressures. We'll discuss it. And some of the different type of manometers are U-tube manometer, well type manometer, or incline type manometer. We'll discuss about all these things. And in the other part, we have some devices which is used to measure the dynamic pressure conditions. Under this, we have three different configurations. One is diaphragm type, second is bellows type, third is Bourdon tube type. In the diaphragm type, again based on the construction and its working phenomena, we have three different type of diaphragm type of pressure measurement devices. One is flat diaphragm gauge, second is corrugated diaphragm gauge, third is capsule type. And bellows are almost working with the same kind of principle of diaphragm, but here we have a small deviation in its construction and working. But the commonly used or widely used type of dynamic pressure condition, dynamic pressure condition is Bourdon type pressure measurement device. So in this case, we have the C type or helical type or spiral type of Bourdon tube. Bourdon tubes are of three different types: C type, helical type, and spiral type. First, let us discuss about the manometers. So in this manometer, if you just check out, so the U-tube manometer, okay, so which is a simple glass tube made up in the U shape, and this particular thing is very common in most of the laboratory equipments. We might have seen it in laboratory equipments in order to measure the pressure. And the next first level of modified form is well type manometer, or it is simply a reservoir type manometer. So here even the smaller deviation can be measured with this kind of system. You can able to see, I hope. So there the inlet is having comparably more or comparably larger cross-sectional area, and the outlet side is having smaller cross-sectional area or vice versa. So there is a variation in its cross-section. Thereby, this particular thing reflects even a very smaller level of pressure variation. And in the third category, we have the inclined manometer. So the inclined manometer is a thing which is utilizing the fundamental concept of well type manometer, but it is comparably compact in dimension. So wherever we have area or surface or volume restrictions, there we can use the inclined manometer. If we have lesser space, there we can utilize the inclined manometer. Other than that, it uses the same working principle as well type manometer. And the final one is a mercury float manometer, which is almost the same kind of construction, but here we have a float along with a calibrated gauge or calibrated scale. Thereby, the values can be easily seen in a gauge using a needle and calibrated or measurements. Very easily we could able to find the exact value. We don't need to only rely on eyes. Apart from that, we can also use the dial method. Okay, so that is the construction, or it is a modification of the basic type of manometer. So this is the first step, U-tube manometer, as I told you. So here it is very simple, a U-shaped tube. Even we can experiment at the same. You can able to compare the measurement in water levels. Okay, so if you blow air on the one side, obviously the other side the water is getting replaced. That is the fundamental concept of U-tube manometer. Here, as in all these manometers, water and mercury can be used. So here we have a smaller animation. You can able to see, I hope. So very easily the working is demonstrated here. Okay, so when we have lower pressure, obviously there is a suction. This suction leads to a pressure difference, and if it is higher pressure, obviously there is a fluid rise in the other side of the tube. So this also leads to a pressure rise, which is designated with the parameter H. That is, so it is del P, which is equal to rho G H. Rho is density, G is acceleration due to gravity, H is the height which we are designated to, and del P is the difference in pressure. So this is what known as the functionality of a manometer. Thereby we can very easily find out the values. Then next we have the well type manometer, which uses the same working principle. The only difference is here we have the varying cross-sectional areas. Thereby even a very little pressure variation can be easily measured. Then next we have the inclined tube manometer. So in this inclined tube manometer, which again uses the same principle of basic manometer, but here the construction allows it to fix in compact spaces. So that is what the thing known as inclined tube manometer. Then we have four summing devices, or the devices which are used in dynamic conditions. Okay, as I have shown you in the classification chart, here we have three different constructions. One is diaphragm type, second is bellows type, third is board and tube type. So first of all, let us start with the diaphragm type. So in the diaphragm type of pressure measurement device, so here we have a diaphragm which can even sense a pressure from within a range of 0 to 4 mm. So the deviation in the diaphragm is somewhere around 0 to 4 mm. That is sufficient to uh, measure the pressure variation in a given system. Okay. So the diaphragm can be of different type. One is flat type, as shown in the picture. It is a flat diaphragm. Next is corrugated. Corrugated in the sense it is a kind of zigzag manner thing. So which can very easily find out the minor variations also. Then capsule type. So in the capsule type, we have already the thing filled inside. The air is filled inside. So it is even more sensitive to even smaller variations. Those variations is sufficient to give you the maximum accurate value. And here, since it is a capsule type, it can also arrest the minor unwanted vibrations. So the precision of this equipment is also good. So this is how a diaphragm gauge works. So here we have an animation along with the construction. So here we got a dial along with the bolting system and sealing. So you can easily see the construction of the thing. The blue colored one is nothing but the diaphragm. The blue colored thing what we can able to see in the picture is diaphragm. So this diaphragm, when the air coming in, no, so obviously it pressurizes, and the stem which is associated to this moves the dial to move in the, or needle to move in the dial. So this is how it functions. Yeah. Now let us go to the next slide. So here we got the bellows type of thing. Yeah, so here we got the bellows type, second type. So the bellows type functions in around almost in the same kind of construction, where we have the flexible bellow construction along with the retention springs. So these springs are sufficient to hold or bring back the needle to its original condition. And next we have this, the animation of a bellows gauge, how it functions. You can able to see, I hope. So when the pressure comes in, the bellows are getting expanded against the spring force. So when the pressure is released, the spring force or spring resistance is sufficient to bring back the needle to original position. Next, we are moving on to the third important thing, which is known as the board and tube. So the board and tube is one of the important equipment which is widely used in many of the gauges because of its precision and accuracy. So the construction is simple, but here we got a metallic tube, and this metallic tube which is functioning based on the elastic limit. So as we seen in the strength of materials, we got the Hooke's law, and this board and tube is a thing which properly obeys Hooke's law. Thereby when the pressure is increasing, obviously it is getting deflected, and once the pressure is released, obviously it is getting back to original position, and it is also supported by spring force. So let me show you. So here we got the animations of how it is working. So that we can able to very easily see that the board and tube, which is the C type tube, which is shown in red color, and that particular thing, when the air is getting filled via this path, obviously it is getting elongated, or the profile is getting varied. So because of this thing, the link along with sector and pinion setup, this is vary or deviating from its original condition. This condition is sufficient to move the pointer is again moving on a graduated scale. Okay, this is the graduated scale. Thereby, very easily we can able to measure the pressure in a gauge. So the same thing is demonstrated in the second picture also. So very easily we can able to see. So when air is coming in, this is getting elongated. You can able to see, I hope this is elongating. Because of the same, the minor movement is converted to a major movement with the help of a small gear train, and that is connected to the needle. Thereby the values are easily visible. So this is how a Bourdon tube functions. And the second type of construction of Bourdon tube is helical type Bourdon tube. So here the construction is very simple to the C-type Bourdon tube, but here to have even more accuracy in its working, so here the Bourdon tube is of a helical style. So here you can able to see it is following a helical path. Thereby, even the smaller variations, even the smaller variation of air is sufficient to make a minor variation that is sufficient to move the pointer to a little bit. Say for example, instead of measuring measuring with a least count value of 1 bar, with this particular thing we can able to measure from 0.1 bar, 0.2 bar, like that the least count value even more reduces. Thereby Bourdon tube. So this also functions with the same basis of helical tube, but here we got a shaft kind of setup, so it is even reliable. So since we got the Bourdon tube supported by a shaft, here the vibrations are less, and the vibration of the system is almost damped in the system. Thereby the pointer is moving in a proper streamline motion, or the movement of the pointer is even more settled. Thereby very easily we could able to measure the exact value. Now we are moving on to the next important topic, which is the Bernoulli's equation. So the Bernoulli's equation is one of the important equation which is used in fluid mechanics, and which uses three different type of energies. So it is simply the sum of three different energies in a given condition. So the condition is based on different assumptions. The first assumption is it is the fluid is ideal and incompressible. So the fluid is ideal and incompressible. So we all very well know about the condition of ideal fluid, I hope. So an ideal fluid does not have any viscosity. So in a practical term, if you take, so there is no such fluid, because no fluid, even it is based on the gas or liquid, it should possess a little, at least a little amount of viscosity. So that is a practical or real fluid. But as per the concept, the ideal fluid will not have any kind of viscosity. So this is in practical case we are even using it for um, hand things based on flow. One is the flow is steady flow. Steady flow in the sense there won't be any velocity variations with respect to its time. Okay, with respect to time, there won't be any velocity variation. That is what the meaning of steady flow. Then the flow is continuous. So there is with the consideration of all these assumptions, the sum of pressure energy, kinetic energy, and potential energy. This is constant along a streamline of fluid flow. So that is the statement of Bernoulli's equation. Let me repeat it again. The equation states that in an ideal incompressible fluid, when the flow is steady and continuous, the sum of pressure energy, kinetic energy, and potential energy is constant along a streamline. So in a mathematical form, P by W or P by rho G, W is nothing but specific weight or weight density. So P by rho G can be also written here. Rho is mass density, G is acceleration due to gravity. Then V square by 2G. Here V is velocity of or mean velocity of the flow, and by G is, as we know, acceleration due to gravity, and Z is the reference datum distance from the reference line. Actually, it is the distance of the elevation from the reference line. So if the flowing fluid has inclination in the path, so obviously it will have a height difference from the datum line, that is designated as Z. So this is the mathematical relationship what we have with the Bernoulli's equation. And next we are moving on to the applications of Bernoulli's equation. So the Bernoulli's equation, it is directly used in various applications, and these applications are directly used in most of the automotive or mechanical or aerospace applications. Especially it is most widely used in aerospace applications, especially the last one. The pitot tube is a very important equipment which is used in flights, that we are going to see along with the along with images. Let me go to the first type of equipment, which is the venturimeter. So the venturimeter looks like the same, which is shown in the picture. So it is a device which is used for measurement of flow in a pipeline, and it is based on Bernoulli's equation that we all know. So it has three different parts. As long as the construction is concerned, we have the three different parts. So one is the converging part or converging cone. Second is the short cylindrical throat. Third is the diverging cone. So all the three setups or all the three sections serves for different purpose. Let me explain it. So first part is the converging cone. So in this converging cone, we have the cross section is uniformly reducing. Thereby, since the cross section is reducing, the pressure increases. The pressure along with velocity also increases. When pressure increases, obviously the velocity also increases. Thereby, this pressure and velocity increase leads to create a pressure difference between the pipe flow and the reduced fluid flow. Let me explain. Yeah, so this is to create a pressure variation. Okay, so the normal angle of converging cone is between 14 degrees to 20 degrees. So as far as the examinations are concerned, whether it is gate examination or any type of interviews which considers fluid mechanics, these kind of values are important. So the converging cone is normally of 14 degrees to 20 degrees. Next, we are moving on to the next part, which is the throat. This throat is the shortest path for fluid flow. So why it is provided? It is to create the pressure variation. Only if we got a proper settled area, then the flow again will come to the original streamlined condition, or as per the Bernoulli's theorem, the flow should be steady and continuous. So in order to ensure the case, we have this short throat area. So here the reduced cross section, which in turns increases the pressure and velocity, that is getting settled in this particular throat area. So the throat area is normally based on the aspect ratio d by d. Small d is the diameter of throat, capital D is the diameter of the pipe or inlet. So this particular thing should be between 0.4 to 0.7. Yeah, next we have the third important part known as diverging cone. The diverging cone part is required to again bring back the fluid flow to original condition. Since we are only measuring the particular fluid flow using the venturimeter, it is a main duty to bring it back to the original pressure and velocity condition. Thereby only it won't get affected by the atmospheric pressure value, or if it is working with the extreme or increased pressure value, that is highly impossible to bring it back to the original flow, reduce the velocity and increase the pressure. Thereby concept. So the converging is even more drastic than the diverging. Divergence is taking place in a slow and steady pace. Then some major applications are, it is mainly used to find out the discharge of any gas, liquids or slurry or suspended oils or any other kind of processing fluids. Even the molten form of plastics can be measured. So it is used in various cases. And because of this smooth sloping design, so even it is suitable for dirty fluids, contaminated fluids or dirty fluids, sludge, slurry, anything can be measured with the help of the venturi meter. Since we have the construction, we got many advantages. So first of all, here the high pressure recovery is possible. Since we have the diverging cone area, it is sufficient to bring it back to the original condition. Then high coefficient of discharge. So here the coefficient of discharge value is high, so no need to worry about the working operation parameters. So obviously, since the coefficient of discharge value is less, so coefficient of discharge is high, obviously it will have lesser deviation from the original value. Then smooth slope helps in measuring dirty fluids that we have discussed. Then it can be installed in any direction. This is a very important advantage of this particular venturi meter. It can be fixed as a horizontal equipment or inclined equipment or even a vertical equipment. Then it is more accurate in measurements. But some of the disadvantages are, it is cost wise and size wise it is large, so it is costly as well as it is rely only on the linear values. Then the distances, then maintenance is not easy. That is why the inspection is also not easy. Then it cannot be used for smaller pipes which have the diameter lesser than 70 mm. Yeah. Then so this is how the schematic arrangement of or schematic working of a venturi meter will look like. So since the cross section is reducing, so obviously the pressure increases as well as velocity is also increases. Then in the throat area it is properly settled, and again in the diverging part, again it is bringing back to original condition. Then we got the orifice meter. So the orifice meter is the little modified form of venturi meter, so which almost uses the same kind of working principle, but the setup is very simple. So you can able to see the cross section of a orifice meter. So here we don't have any kind of additional converging diverging kind of setups. Simply we have only one orifice. So this blue color one is the orifice, so which is of a crosswise inlet, so thereby it simulates the condition of a venturi meter. It is not exactly the condition of venturi meter, but it simulates. So the fluid comes in and it is getting deflected, and it is almost following the same kind of fluid flow as in case of our venturi meter. So the fluid comes in, the velocity increases, settles down, again the velocity is getting back to original condition. But here we are supposed to note one important thing. So here the reduce or a reduction or reduced narrow area is not happening here. Instead, the reduced area is happening somewhere else. This particular area is known as vena contracta. So this is an important parameter in venturi meter. So the reduced area is not happening in the exact knife edge of the orifice plate. Instead, it is taking place just apart from that. So this particular area is known as vena contracta. So this is because of the inertia created by the fluid flow. So here we got the sentence about the vena contracta. Vena contracta is defined as the narrow central flow region of a jet that occurs at or just downstream to the orifice of a valve. It is characterized by high velocity laminar flow. So here the flow is laminar and it is of very high velocity. The peak velocity takes place only at vena contracta. So here the discharge is given by the formula Q is equal to CD into A naught into A1 root of 2GH divided by A1 square minus A naught square. Here negatives. First thing is yeah. So some advantages are it is cost effective and quite easy to use. Then it occupies lesser space. So it is very easy to work in constrained applications, and it can be used to find out the flow rates of larger pipes even. Then it can be installed in horizontal or vertical positions. Sorry. Yeah. And some applications are it is used in water treatment plants, natural gas industries, or refineries, or petrochemical plants. Yeah. Next, we are moving on to the differences between venturi meter and orifice meter. First of all, the venturi meter and orifice meter functions on the same kind of working principle, but there are some important differences based on their working principle and construction. First thing is venturi meter has three different areas: converging area, throat, and diverging area. Whereas in orifice meter, it is a single simple thin plate. That's all. And the pressure loss in venturi meter is only 10%, but in case of orifice meter, the pressure loss is around 50 to 60%. And coefficient of discharge of venturi meters, as I told you, it is very high. So there is lesser possibilities of deviation from the actual value. So it is 0.98, but in orifice meter it is 0.6, which is comparably giving us the maximum kind of deviation from the actual or cost of venturi meter is on the expensive side, and orifice meter is comparably cheaper. Next, we are moving on to the next important equipment known as rotor meter, or it is also sometimes known as flow meter. The rotameter is a device which uses the pressure of fluid, which is making a flow to move up and down on a calibrated scale or graduated scale. Thereby, the flow can be easily measured. It is a simpler equipment, but most effective kind of equipment. So in the animation, very easily we can able to see the float which is flowing or floating because of the fluid's pressure. Since the pressure is pushed from the bottom side, the float is floating. Thereby, you can able to see the graduated scale, which shows us Oxygen applications. So it is normally used to find out the gas flow measurement, or it is used for rotating equipment flow measurement, or in process analysis, or in high pressure flow on offshore oil platforms, in chemical injection, or purge liquid or gas metering. So this is what I told you, the gas metering that is taking place in the oxygen systems. Yeah. So now let us go back to the slide to know that various disadvantages of rotameter. First of all, the viscosity. The first point depicts that the viscosity of fluid affects the functionality of rotameter. This is a very important thing. Second thing is the rotameter is based on working principle, or it is functioning based on the gravity. Even it to bring back to original condition, gravity serves. So the restriction is it can be only used in the surface of Earth. Thereby, it will give you the exact value because the systems are calibrated for Earth's gravitation value. So it is not possible to use in space or in some other places. The next thing is the direct flow indication is relatively poor because it is not showing you the exact values. This is the most economical and cheapest form of system. Thereby, it is not used in high accurate kind of conditions. And the float is flowing through a medium. So, in order to get it to an electronic signal, say a separate electronic transducer is needed. So that then only it is possible to measure it or bring it to any kind of electronic systems. Then the rotameters are not easily adapted because of the construction of its own. And next thing is the size is not sizes are restricted to 6 inches or 150 m. So more than that, or if the flow is more, it is highly impossible to use the rotameter. Yeah, let us move on to the next important equipment, which uses the principle of Bernoulli's theorem, which is nothing but Pitot tube. So, which is one of the most important equipment for aerospace industry, which is invented by French engineer Henri Pitot in the in the years of mid 19th century. So, this is how a Pitot tube will look like, and there is a picture even showing us where and how the pitot tube is fitted on a commercial aircraft. So this is how the pitot tube looks like. So here the main concept is the pressure energy is getting converted from kinetic energy of moving fluid. Let me explain it easily. So just consider this pipe of moving liquids or fluids. So the fluid is getting inside with a particular mean velocity. So in these free areas, there is no restriction. So the flow is simply taking place with the same velocity. But in this particular part or in this particular point, yes. So the fluid comes in and it hits this particular region and it is getting obstructed or it is getting stopped by the inserted pitot tube. So here it cannot move further. So what happens now? The kinetic energy is getting converted to pressure energy. Thereby, the pressure is making it to increase the water's level. So this is how a normal value of water level is maintained. This is the stagnation pressure. But here, if you just check out, here we got the increased pressure value. Okay, this particular thing is because of conversion of kinetic energy to pressure energy. That is why it is mentioned as V square by 2G. So this is the default pressure, but this is the elevated or increased pressure due to kinetic energy of fluid. So this particular region is directly equal to V square by 2G. That we'll check out in the next few slides. Yeah. So by proper solution, we could able to arrive that V is equal to root of 2G into Hs minus H naught. Hs is uh, yeah the pressure or the static pressure's height value, and sorry, a stagnation pressure's height value, and H naught is static pressure's height value. So this is what I told you, the difference. So here we got the stagnation pressure from the center of tube to maximum height, but the static pressure is simply when the outer if the pipe is fitted to the outer edge of the flowing fluid, obviously it will reach a static pressure value, because there the water is not that much flowing. So that is known as the static pressure, and this is the stagnation pressure, which is caused because of the working fluid's velocity. Yeah, next. So with this, we are moving on to the next topic, which is the hydraulic machines. And under hydraulic machines, we have two different type of hydraulic machines. First of all, we have uh, turbines. We have two different type of equipment. One is turbine, whereas the other one is pump. First, we'll discuss or we'll start the thing about turbine. So the turbine or hydraulic turbine is basically from a simple concept known as water wheel. So here the image of water wheel is shown. So you can able to see the flowing water's velocity is getting converted to uh, a rotational energy. Thereby, it is used for any other applications. So nowadays we are using it for power or electricity generation, but in olden days they used it for grinding, grinding to get the powder. Say for example, wheat is getting grinded to get the wheat flour. In some situations, they use the power of flowing water. Yeah. So from this concept, we could able to understand that hydraulic turbine is a prime mover which uses the energy of flowing water and to get converted or to convert it to mechanical energy. So the hydraulic energy of this is how we can able to harvest the power of. Is known as penstock, which brings water of high pressure and velocity to the turbine's range or turbine's working range. So here, when the high speed water hits the turbine blade, it rotates, and a generator is connected with the same shaft, which is sufficient to produce or which is sufficient to convert the mechanical energy. we'll discuss about based on how the based on head how the turbines are getting classified. So the head is nothing but the high difference of water's origin from the turbine level. So this is mostly suitable for hilly regions. In most of the hill regions, the water is flowing on a mountain path or between two mountains. But normally the hydel power station is normally fitted or which is installed in the lower part of the mountain. So the high difference between the turbine level to the particular water dam level is comparably high. So in this case, the high head turbines are used. So a good example of high head turbine is belt and wheel turbine. And in the medium level category, we got the Francis turbine, which in which the height head is between 60 meters to 250 meters. And the third category is low head turbine. In this category, we got the Kaplan turbine, in which the head is between 15 to 60 meters. And the next category is very low head turbine, where the head is less than 15 meters. So this is not that much used in practical commercial cases. Only the belt and wheel, Francis turbine, and Kaplan turbine are used in these cases. So this is what I told you. So the low in a low head turbine, it is mostly installed in plain regions, plains or flat terrains, and the medium head is normally used in flat terrains or in some hilly regions. And the third category, high head, is mostly fitted in hilly or mountain regions. So we use Kaplan turbine. In case of medium head, we use Francis turbine, and in case of high head, we use belt and wheel turbine. Yeah. So let us move on to the next category. It is based on hydraulic action of water. So what is hydraulic action of water? So if the water is or the water's energy, the water's kinetic energy is only with the kinetic energy, then it is known as impulse turbine. But along with kinetic energy, if pressure energy also utilized for the same purpose, then it is known as pressure energy. Sorry, reaction turbine. So in impulse turbine, only the hitting force or the kinetic energy of conversion to mechanical energy, whereas in case pressure energy comes to play, thereby it is helping to convert the energy from water's energy to mechanical energy. Yeah, so this image easily mentions us. So in case of impulse turbine, only the hitting action or the kinetic energy. So it or the wheel. So only the hitting force is utilized for energy conversion. Whereas in case of reaction turbine, see, there is a smooth flow of fluid, thereby very easily the smooth flow is sufficient to slowly move the rotating turbine, which is also because of the kinetic energy along with pressure energy. So this is how a reaction turbine functions. Yeah, next we move on to the next thing. Based on hydraulic action, so the kinetic energy of water to get converted from to get from hydraulic energy to mechanical energy. And in case of reaction turbine, that I'll tell you, impulse action turbine is working. You can able to see from the first image, water is hitting, and the hitting force is sufficient to rotate the wheel. The system. Yeah. So this is how a Pelton wheel turbine looks in actual practice. Next, next we move on to the reaction turbine category. In this reaction turbine category, we have all the other three turbines are coming under this category. Francis turbine, propeller turbine, and Kaplan turbine are the other three things which we use in a reaction turbine category. In this case, we use kinetic and convert the hydraulic energy of water to mechanical energy. Next, we move on to the reaction turbine with a simple working animation. So you can able to see a hope. So when the water's level is getting increased, obviously this pressure variation creates uh, or pressure variation is created inside this volute chamber. So this pressure variation is sufficient to rotate the impeller blade, and this impeller rotation is converted or it is connected to a generator to harvest electric power. Yeah, so this is the image of a Kaplan turbine, one of the reaction turbine used in commercial space. Yeah, next is based on the direction of flow. So here we have three different type of directions. One is the radial flow. The only radial flow turbine what we have is Francis turbine. Francis turbine is the only turbine which uses radial flow. Why it is known as radial flow? When water gets in, yeah. So in the middle of the casing we got the runner. So because of the same, water is entering to the runner in the radial direction. The water is entering to the runner in the radial direction, thereby it rotates. So that is why this is known as radial flow turbine. And only type of turbine coming under this category is Francis turbine. Next, this is how it works. Next, we got the axial flow turbine, so which is nothing but the Kaplan turbine. So in the Kaplan turbine, although it looks like the same in construction, it is highly impossible to observe. So this spiral casing or volute casing is used to increase the pressure and velocity. But see, the water is flowing in the downward direction when it hits the propeller blade. So after rotating in this particular case, after rotating in the particular case, water is getting inserted or water is getting in to make contact with the rotating runner or propeller only in the axial direction. So in case of our uh, radial flow turbine, the runner was in the middle like this. The runner was in the middle, so the radial flow is sufficient to hit like this. But in this case, in order to hit this propeller, water need to come down in axial direction. So water is coming down in the axial direction, thereby it rotates. So this is the concept of axial flow turbine. Two turbines are coming under this category. One is Kaplan, another one is propeller turbine. These are the two different turbines coming under the category of axial flow. This is how it functions. is the only impulse turbine available. Second thing is it is used for very high heads like the mountain regions. Third thing is this turbine uses the tangential flow. This is tangential flow. So these are the three different 1870 and this it is used for high hits as I told you. So some of the specifications are it the power range generation capacity is about 400 megawatts. Speed is ranging from 65 to 800. The efficiency is about 85%. Runner diameters are between 0.8 to 6 meters. When you just check for the construction, only there are four important parts. Nozzle and spare, second is runner and bucket, third is casing, fourth is the braking jet which is to stop it. So here you can able to see the construction. So here we got the bucket and we got the Pelton wheel and here we got the nozzle, and to control the nozzle we got the spear valve, and this is the adjustment for the spear valve. So very easily the water is coming in, forcing it in the tangential direction, thereby the turbine rotates and it is connected to a generator. Please wait guys, there is a loss of network connection.